So our section, get this on here, 7.6 is about binomial expansion. And it's possible that when you were in Algebra 2 you learned a little bit about expanding using Pascal's triangle. Well, the approach we're going to take today is using the binomial formula with combinations. It's kind of an exciting lesson, and it's probably one of the harder ones we've done, but that's all right. We're up for the challenge. So to expand a binomial, a plus b to the nth power, it wouldn't be that bad if it was the second power or even the third power, but once you get beyond that, it's kind of elaborate. So we have a way of using combinations and a summation of a sequence or a series to calculate certain terms, or possibly all the terms, using our calculator as well. And we're going to use our calculator to find our coefficients, so that's going to be extra nice. So there's a set of steps, and go ahead and write these down for now, even though you've never actually seen this yet. First step is we're going to set up our sigma notation. So depending on the problem and the binomial that we're expanding, we're going to set it up. Step 2, we're going to program our y equals menu with the sigma notation, basically, so we can find our coefficients. All right, step 3, we're going to write down the coefficients once we find them. And we're going to find the coefficients. I'm just going to use the table to go pluck them out. And then step 4, we're going to add in our variables. And that part's actually the easy part. The programming the calculator is pretty tricky, and that's going to require you to set up the sigma to begin with. So let's start with, whoops. Sorry, I'm not quite sure how I'm supposed to get that thing out of there. Oh, well. Click on it. Maybe that helps. Nope, not at all. Okay, we're going to expand x plus y to the 6th power, and we're going to use our binomial formula. So if for some reason you know another way, that's great, but I want you to try this method because it's going to piggyback off of our use of combinations. Now, let me go back a second. I kind of skipped over the formula. This is the sigma notation formula. And a couple of notational issues. We always put the bottom of the index underneath the sigma. So k is going to go from 0 to n. And then this is an interesting idea. They write the combination in that weird parenthesis notation. So remember, nk in parentheses means n combinations of k. But then it's going to be whatever the a, the first part of the binomial, whatever this guy is, to the n minus k power, times b to the k power. And that's to find any particular term, and then when we sum up all the terms, we're going to get the expanded version of our binomial. So let's see this in action. Our first step is to write our sigma notation. So sigma goes from k equals 0 and then up to 6. This number right here is always going to be our n if we're expanding. And then in the combination, we're going to do a general form of 6 taken k times. And the reason I'm keeping k general is because we're going to expand the entire binomial, so we're going to want every single coefficient. And then x is my a value, this guy right here, so we're going to take him to the 6 minus k power for any particular term, and then y, so times y to the k power. You'll get used to this, it's just kind of funky. Now, on my calculator, this is where it gets kind of exciting. I'm going to go to the y equals menu and write this down on your paper before we actually go ahead and set this up. On my calculator, we're going to set up 6 in y equals 6 combinations of x. Remember, I have to use x as the variable in my calculator, times, and then we have, this is what gets kind of weird. I just want the coefficients. So the coefficients of my a value is just a 1. So I have 1 to the 6 minus x power times, and then another 1, really boring, to the x power. So let's pull up my calculator and I'll show you what this looks like. So 6 combinations, same place we always found combinations, taken x times. Now this one's going to be a little boring because they're 1s as our coefficients, but that's okay. 6 whoops, I already forgot parentheses. 6 minus x power. I wish I had an easier way to type this. Times, and we're going ahead and writing the 1, even though I know it's really boring, just for the sake of procedure. So 1 to the x power. Now, this is all going to be stored into my table, because I have my table set up that way. So when k equals 0, my coefficient is a 1. And remember, we're supposed to take it all the way up to a 6. So what I'm going to do now is I'm going to write out these coefficients all the way through 6. So I have a 1, I have a 6, I have a 15, leave a little space, I have a 20, I have a 15, I have a 6, and I have a 1. And now the fun part. That was my coefficients that I wrote down using my calculator. Now I need to figure out what variables go on top of these, or next beside these coefficients. So for the first coefficient, when k equals 0, think about plugging in a 6 minus 0, that would be x to the 6th power. So this is x to the 6th power, and then y to the 0 wouldn't be anything. Plus 6 times, if I put a 1 in for the k, that would be x to the 5th power, and then putting a 1 in here, that would be y to the 1st. Plus, and you're going to notice something kind of pattern-like happening. This is going to be x to the 4th, y to the 2nd, plus x to the 3rd, y to the 3rd, plus x to the 2nd, y to the 4th, whoops, I ran out of room, plus, this is y, oh geez, try again, Abruzzo. That was a 6, I believe. Now it's going to be x times y to the 5th, plus, and then I covered up the 1, sorry, 1, and then finally no x's, but we're going to have y to the 6th power. So notice every time I took away an x, I added a y in there. And that's how these are going to work, binomial expansion. There you go. Good time. All right, glad we didn't have to FOIL that out by ourselves. That would have been really gross. All right, let's try the next question. X plus 1 taken to the 5th power. So my general sigma notation goes k equals 0 up to the 5th. Oh, 5th power. I don't know if I spoke wrong. And then combinations of 5 taken k times, which we will set up on the calculator. And then I've got x to the 5 minus k times 1 to the k power. That's not going to be very exciting at all. Okay, there's not two variables in this one, so this will be a little easier. On my calculator, I'm going to have to put this general sequence into y1, series I should say. It will be a series, but it's going to start out as a sequence. So we have 5 combinations taken x times. Now remember, I just want the coefficients here for the calculator. So the coefficient of x is a 1. So 1 to the 5 minus x power times 1 to the x power. This is going to be a really boring sequence, but it doesn't matter because we're going to make the calculator do the work. I'm going to cheat. I'm just going to use the old one and kind of type over it. 5 taken x times 1 to the 5 minus x power, and then 1 to the x power. So going back to my table, we're going to go all the way out to 5, this time starting at 0. So my coefficients are a 1, and then a 5, and a 10, and a 10, and then a 5, and then a 1. And now for the fun part, I'm going to take these coefficients and I'm going to slap variables after them. So using my general form, if I start with k equals 0, 5 minus 0 would be x to the 5th power, which doesn't surprise me. And then nothing else after that. 1 to any power is just going to keep giving me a 1. So this is actually a really easy one. It's just going to be x to the 4th, going down to x to the 3rd, going down to x squared. The 1 is not doing anything, so I'm not even bothering thinking about it. X and then the constant term. Okay, moving on. Okay, this one's going to be a lot more exciting because we have 2 variables and 2 different coefficients that are going to really affect our coefficients of our polynomial once we expand it. So general form, sigma notation, k goes from 0 up to 4. Good news, only have to do 4 terms. Combination, 4 taken k times in general. And then here it gets really exciting. 3p to the 4 minus k power times negative 2p to the k power. So on my calculator, remember we're programming the calculator just for the coefficients. So we're going to start with 4 combinations taken x times, now watch your parentheses. You probably don't need parentheses around the 3, because we're not going to type in the variable of p, just 3. But up in the exponent, remember, it's going to be 4 minus x times, and then careful, this is a -2, that does need parentheses, well, kind of, depends on your calculator, to the x power. Alright, let's program this. Okay, let's see if I can cheat a little. 4 combinations taken x times, 3 to the 4 minus x power, and then here I need parentheses around my -2 to the x power. Okay, go to my table and let's pluck out the coefficients. Starting at 0, I've got an 81. Ooh, -216. So it takes care of the signs for me, so that's cool. +216, -96, and 16. Okay. Now my variables that go along with my coefficient. Let's get those guys. So if I were to, into this general form, put a 0 in for my k's, that would be, don't worry about the 3, let's talk about the p. P to the 4 minus 0 would be just p to the 4th. And, oh, this was a q, Abruzzo, nice try. Sorry. Q to the 0 power is nothing that's going to affect that term. Okay, next term. This is going to be p to the 3rd, but now we have a q to the 1st, plus, this will be p squared q squared, minus p q to the 3rd, plus, and then finally q to the 4th. A lot of nice symmetry when you expand these binomials. It's not too bad once you get the hang of it. Okay, more fun. So in general, we have k goes from 0 up to 3 this time only. And my first combination is going to go from 3 taken k times. And then my first term is 2m to the 3 minus k power times -5n to the k power. So on my calculator, to just calculate the coefficients in my y1, I'm going to set up 3 combinations taken x times coefficient of 2 only to the 3 minus x power times, be careful, this is a -5 to the x power. So again, on the calculator, it's important that you guys practice writing these out. I know they're not a lot of fun. 3 combinations taken x times, base of 2 to the 3 minus x power, and then what was it, a -5 to the x power? Okay, I'm grabbing just 0 through 3 this time for coefficients. Where are we at? Yep. So we have 8, -60, we have 150, and we have -125. And you're going to notice that after you hit a certain point in the sequence list, you're not going to have any more coefficients because there aren't any. Alright, now for my favorite part, we're going to add in the variables. So starting with k of 0, that would be m to the 3 minus 0, or m to the 3rd power. And then we're going to take 1 away from the m and give an n, plus, and then, oops, 1m and 2 n's, minus, and then 3 n's. Alright, good times. It's going to get exciting after this. Now they're going to give us very specific instructions. They're going to give you a binomial sort of to expand. They don't want the whole thing though. They just want to know the term that contains x to the 9th as a variable label. So what that tells me is if I think about my binomial formula, you know, k equals 0 to 14, oops, 14 combinations taken k times, yada yada, x to the 14 minus k times 3 to the k. So what that tells me is if I want x to the 9th, that means 14 minus something needs to give me a 9. I think that something is my k must be equal to the number 5. So I'm going to just want to find the fifth term when k equals 5. I don't have to do the whole binomial expansion. So I just want that exact one term. So if k is 5, that means if I take my general form and I put a k in for 5, I get 14 combinations taken 5 times, x to the 14 minus 5, which will be 9 of course, times 3 taken to the 5th power. So on my calculator, I'm not going to worry about the x to the 9th because I know what that is, but I'm going to type in 14 combinations of 5 and then 3 to the 5th power because I don't really know what that is. I could do a sequence, but I'm going to do it on the home screen. 14 combinations of 5 times 3 to the 5th power. It's going to be some lovely number, I can tell. Oh yeah. Yikes. So I'm really happy I didn't have to expand that, especially by hand. The coefficient is 486, and then x to the 9th. That'll be that term. So somewhere in that huge binomial that I luckily didn't have to expand, that would have been the term they were looking for. Okay, moving on. This time I want the y to the 8th term. So I'm going to kind of rearrange this because I don't really appreciate the order in which it is listed. I'm going to say y plus 2. It doesn't really matter. I like the variable first. So again, I'm going to set up a really general sigma notation. K equals 0 to 14 in this problem. 14 combinations taken k times. Y to the 14 minus k times 2 to the k. So if I want this to be y to the 8th power, that must mean I need to take away or subtract 6, so my k must be a 6. All I need to do is find the one term where my k is a 6. So 14 combinations of 6. I already know this is going to be y to the 8th, but let's write it anyways. And then 2 to the 6th power. So on my calculator, in the home screen, we're going to type 14 combinations of 6 and then multiply it by 2 to the 6th power. I think I already did this one, so I'm going to cheat. 192, 192. Isn't that cute? Y to the 8th power. All right. The next question has you find the 4th and the 16th term. Now, this is a little different question. They don't say like what exponent you want on the variable, but they tell you they want the 4th and 16th term. Now, I don't know if you noticed, but each one of these sequences started when k equals 0. The index started at 0. So if I want the 4th term, that means my k equals 3. And if I want the 16th term, that means my k equals 15. So we're going to expand this guy, just 2 terms of it. So the general form, of course, k goes from 0 up to 20. And then 20 combinations taken k times. We'll separate each term in a minute. X to the 20 minus k power, and then negative 2 to the k power. So when k equals 3, that's going to give me, and I'm going to write it like I'm going to write it on the calculator, 20 combinations of 3. Obviously this will be x to the, yeah, I'm good. I got a little confused for a minute, but I'm good. X to the 20 minus 3 power, which will be the 17th. So x to the 17th is my 3rd term. And then it's going to be negative 2 to the 3rd power. So on my calculator, I'm going to type this part and this part in, because I know what this is. And I think that gives me negative 9120 x to the 17th. So here's my 3rd term of my sequence. Let's do the same thing for the 15th term now. So 20 combinations 15, x to the 20 minus 15, and negative 2 to the 15. Oh, that's to find the 16th term. Excuse me, I misspoke. So again, I'm going to type this and this part on my calculator. And I'm going to be a big cheater. Oh, this is a huge number. Negative 508035072 x to the 5th power. There is your 16th term. Really happy I did not have to do that by hand. Alright, I think this is our last one here. 5th and 12th term. So if the 5th term is what you're interested in, then you want to know when k equals 4, and then the 12th term will be when k equals 11. Setting up my general form. K goes from 0 up to 18 on this binomial expansion. 18 combinations of k, u to the 18 minus k times, careful, negative 1 to the k. So for the 4th term, fifth term, when k equals 4, I'm going to be doing 18 combinations of 4 times u to the 18 minus 4 times negative 1 to the 4. And again, I'm a big cheater. I already did this on the calculator, and I got 3060 as my coefficient, and then of course u to the 14th as the variable. There is your fifth term. Okay, same idea for 11. 18 combinations of 11 times u to the 18 minus 11 times negative 1 to the 11th power. That says negative 1 to the 11th power, for those of you who can't read my scribble. On my calculator, because I'm a big cheater, I already did this. This is negative 31824 u to the 7th power. And that is your very fun introduction to binomial expansion through the use of combinations to find your coefficients. Good luck on your bookwork. It's a hoot. That's the end of our chapter 7, in fact, so get ready for a test.